Okay, welcome to chapter 6. I've got good news and I've got bad news. So, good news is that this is going to be super hard to understand, mind blowing, amazing, uh, really powerful theory stuff. The bad news is you only need to know a little tiny piece of what we talk about. Um, you might think those two are reversed, but I think it's bad news that the AP curriculum doesn't have more molecular orbital theory in it, but it doesn't. Um, but I would much rather you get exposed to molecular orbital theory here in a nice, safe environment with teachers who care about you and a good peer group. Then when you get to college and maybe your professor doesn't know who you are and doesn't care if you understand any of this stuff and drones on and on about molecular orbitals, um, maybe with a heavy accent that you can barely understand, and then gives you impossible tests. So my hope is that you take away from what we talk about here just a little kernel of understanding of what molecular orbitals are, so that the next time you see them, they actually don't seem so intimidating. Um, so we're going to talk about orbital hybridization and bonding, which is really how do we take atomic orbitals and then make bonds. Okay. Um, so some basic facts that you should know. When you want to make a bond, a covalent bond, two neighboring atoms have to overlap their atomic orbitals. Okay. Um, that's essentially the simple level at which you should understand it. Another thing you should know is that we can take those atomic orbitals and we can put them into a mathematical blender and come up with a new set of atomic orbitals that we call hybrid orbitals. And then lastly, there's this thing called molecular orbital theory that really describes this stuff more fully and is really, really powerful to make predictions. We're going to just scratch the surface. Okay. So bear with me for this first part because a lot of what we're going to talk about here is going to be fairly abstract. No. It's going to be completely abstract. And I just want you to do your best to try and make sense of it, recognizing that you're going to be tested on very little of this. There's actually maybe like 2 or 3 slides from this whole thing that are testable, and I'll kind of highlight what those are. Okay. So we've talked about bonding as being sharing of electrons between two atoms. And orbitals we talked about as representing this probability of finding an electron somewhere. So if we have shared electrons, there must be some sort of orbital that is representing them. There must be some orbital that they are occupying, at least in theory. And a lot of times students ask the question like, but how do we know orbitals are there? How do we know they're real? And the answer is, of course, we don't. They are a theory. Just like gravity is a theory. We imagine that if they are there, then we can make some predictions about the way molecules should behave. And if those predictions turn out to be good, then all right, we'll keep believing that they're there, even though they're entirely a theoretical construct that we came up with. So how are we going to use orbitals to talk about bonding? Well, to do that, we have to go back a little bit. All right. And when we go back, we have to talk about what orbitals really are. So you may remember, I think it would have been lecture 2, this word wave function coming up. Okay. Does anyone remember the word wave function coming up before? Okay, let the record show that I'm seeing nothing but blank stares. All right. So perhaps I need a little more space, or perhaps I need to go back. And we can refresh our memories. All right. So I will bring you back to this very simple slide, which hopefully you watch this at some point. So this is the story of how an orbital is born. Okay, orbitals essentially spring from this mathematical construct that maybe someday, if you go on and take linear algebra and three-dimensional, multivariable calculus, and then take some wave physics courses, you might understand the math. But here's the simple process by which an orbital springs into being. Okay, we have this equation we call the Schrodinger equation. It's a mathematical thing. I understood it once in my life. I don't understand it anymore. But I trust that it can be solved, and someone else has solved it for us. Okay, and when they solve it, they get this series of what they call wave functions. Okay, a wave function is a three-dimensional function. So unlike function you're used to, which would be f of x, where you plug in one variable and you get out, you plug in a value for x and you get out a result. Three-dimensional function, you would plug in three variables and then get out a result. The reason we need three variables is, well, we live in three-dimensional space. So if we want to describe a point in space around the nucleus, we need three variables to do it. So we get this series of wave functions. Now, each one of those wave functions represents an orbital. So it's this mathematical thing. I gave an example down at the bottom. So one of the wave functions for a 3D orbital is down at the bottom of the page, and it's got these gross terms in it. This whole first part that I circled in purple, that's just a number, right? Square root of 2 over 81 square root of pi times z over a naught to the 3/2. Z and a naught are just constant numbers, so that's just a number. And then we have a function in terms of r, which is distance from the nucleus, and then a function in terms of these angles related to the nucleus. You don't need to understand any of that. All I want you to understand is there is a mathematical function under there. These pictures you've seen of orbitals that say where the electron is, there is some math in there somewhere. That's where it comes from. So you take one of those orbitals, one of those wave functions, psi 1s or psi 2s, whichever orbital you want to look at, and you plug in a point in space. When you plug in a point in space, it spits out a value. And that value is meaningless. But if we square that value, then we get a meaningful number. Okay? When we square that value, we get the probability of finding the electron near that point. So we have this mathematical function that essentially is telling us where the electron likes to hang out and where the electron doesn't like to hang out. Wherever psi squared has a big value, that's where the electron spends most of its time. Wherever psi squared has a tiny value, the electron spends almost no time there. Okay? So if you want to make a picture of an orbital, what you do is you take points all around the nucleus, you plug them into the function, you square the result, and then you make a map. So when we talk about the 1s orbital being this spherical thing, that came from the fact that, if you plug in all the points around the nucleus, you get a probability that's roughly spherical. So the area where it spends most of its time makes this spherical shape. Other orbitals have different shapes. Okay, but it all comes back to the idea that there is this mathematical function lying underneath. What questions do you have? All right, so So the question is, what is the probability in terms of? And that's a good question. So the probability would be just what you do with that function is you have to do what's called normalizing it. So what you do is you normalize it so that if you find the value of it over all space, it ends up adding up to 1. So if you take the probability everywhere, it adds up to 1. So the value for psi squared is essentially like going to be some tiny fraction that if you take the integral of it, and again this is calculus, but if you take the integral of it all over all space, it would end up being 1. But we don't really need to get into the math of it. All we need to know is addition and subtraction. Okay? So what we're going to do is in this process, we are going to go back to psi itself. Okay? Or we're going to go back to, and by the way, that little pitchfork thing looking there is the Greek letter psi. We're going to go back to the wave function itself, because when you want to make a bond, it means you're combining two orbitals. And when you want to combine two things, what do you generally do with them? Well, we do a simple mathematical operation. How do you combine two things mathematically? You add them together. Okay? So we need to know that there's a function lying under there so that we can then add two functions together. So there is this value of psi at any point in space. It could be positive, it could be negative. Okay? Now, when we put them together, that sign matters. Because if we add a positive number and a positive number, what happens to the result? Is it bigger or smaller? It's bigger. If we add a negative number and a negative number, what happens to the magnitude of the result? It's bigger. If we're talking in terms of magnitude, negative plus negative is going to yield a bigger negative number. Okay? But if we add a positive and a negative, what happens to the result? It's smaller. Okay? So we have these two different ways that we can combine wave functions. They could combine in phase. So in phase means, both wave functions are positive or both are negative. Wherever they are overlapping. Then out of phase would be one of them is positive and one of them is negative. And so wave function will always abbreviate with the letter psi. Which, I mean, automatically all this orbital stuff is cool just because you're using that letter psi, which I don't think there is a cooler Greek letter. So when we combine orbitals, we are going to add them. And we can have two different kinds of results. So I'm going to show this graphically. So here's what I want you to imagine. Graphically, these wave functions might look something like this. So a wave function usually starts with a low value near the nucleus and then reaches some peak and then goes down. Now sometimes it'll go across 0 and then back up and then back down. And then generally when you get far away from the nucleus, it'll have an asymptote towards 0 because as you get further and further away from the nucleus, you're less and less likely to find the electron at some point. So imagine I have two atoms near each other. Okay, we have one here where the nucleus is at the origin, another one where the nucleus is over here on the right. I'm calling nucleus 2. Those would have two different wave functions, and both of them would have that same shape if they're the same kind of orbital. Now, what happens if I add those two wave functions together? Well, from the picture, over here near the origin, this blue function has a very low value. So when I combine the two, really the one plus the other, the red line plus the blue line, is going to look more or less like the red line at first, because the blue one has a value near 0. So I'm going to start out by following the red line more or less. So this is my combined wave function. But then at some point, the value of psi 2 starts to come up. And so what's going to happen to my curve now from combining the two? Is it going to go above or below the red line? Above. So it's going to come up above the red line. It's going to reach a peak right in the middle, and then it's going to come back down. And on the right side, where the red line has very low value, it's going to roughly follow the blue line. The point is there, if I have two things that both have positive value and I add them together, I get a bigger positive number. So adding them together results in a bigger value where they overlap. All right, so now I just have fill in the blanks to recap what we just said. When two wave functions, we call this constructive interference. That's a term that comes from waves. So if you've ever, been in a pool and taken like a boogie board or a float or something and made waves with it, you may know that, if you time it right, you can make one wave that you make end up adding to the prior one. So if you time it right, you can make your waves constructively interfere with each other so they get bigger. All right? So we call this constructive interference. What happens is the magnitude of psi increases wherever the overlap occurs. Well, if the value of psi is going to increase, what's going to happen to the value of psi squared? It's also going to increase. And if you remember 3 minutes ago, which you may not, the value of psi squared tells us the probability that the electron is there. So that means we're now more likely to find the electron there where the two functions overlapped. Now remember, the orbital that we draw, the picture that we draw, is showing us where the electron is most likely to be found. When we draw an s orbital or a p orbital, we're saying, well, this is the area where we're most likely to find the electron. Now, if we're saying we're more likely to find the electron in the region of overlap, what that means in terms of that shape that we draw is that shape is going to get bigger in the part where they overlap. And then since probability has to add up to 100% over all of space, if it gets bigger in one place, it has to get smaller somewhere else. So what happens is the orbital gets bigger where they overlap, and smaller everywhere else. What questions do you have? Joe? So the question is, when atoms bond, and we're talking about the valence electrons, what orbitals do we mean? We mean the valence orbitals. So we mean, if it's something with valence energy level 2, then we'd be using the 2s orbitals and the 2p orbitals to make bonds. Yep. Carrie? So the question is, how is a wave function different from an orbital? They're not necessarily different things. When we talk about orbitals, usually we get that picture in our mind. So when we talk about an s orbital, hopefully you get a picture of a sphere. I don't know how to draw a sphere other than a circle. I'm not good with the little shading. But if we talk about a p orbital, then we think about some sort of peanut-shaped thing. If we talk about a d orbital, then they make these cloverleaf type things. Okay? So usually when we talk about orbital, we mean that picture of where the electron is. When we talk about the wave function, we're talking about the actual mathematical thing that gave rise to it. So like that function that I put up there before with all the sines and cosines and thetas and whatnot, that's what it is. But they are part and parcel of the same thing. So the student question is, if two p orbitals overlap, would one lobe get really big and the other lobe get really small? And the answer is yes. We're going to look at examples of how they actually change. So the next question was, is this one of the slides that's going to be on the test? The answer is no. Okay? I really want you guys to just relax and enjoy this if you can. If you say, I don't want to enjoy this, that's okay. I can't make you enjoy it. But I also don't want you to be intensely worried about really understanding this, because this is a long process to understand. It's really powerful once you get there, but it's a long process to understand. And so I will be highlighting exactly what it is you need to know. All right, so what if instead one of my functions was positive and one was negative? So I took the same two graphs from before, but I made psi1 a positive number and I made psi2 a negative number. I want you to take a moment and draw what you think psi1 plus psi2 would look like in that case. So when I start out near the origin, what is my purple graph going to look like? It's going to look like the red line to start. Okay, so I start out following the red line. But at some point, that blue function kicks in. And what's that going to do to my line? It's going to pull it down. All right. So now it's going to be underneath the red line, and maybe a little closer to it than that. But it's underneath the red line to start. And eventually we're going to reach some point in the middle where what happens to the two functions? They cancel each other out completely, and we are going to go through 0 at some point, and on the other side we're going to have kind of a similar thing. You may or may not remember this term from before, but this is called a node, where it goes through 0. If you're trying to make a bond, having a node between the two nuclei, that's a bad thing, because that means there's no electrons between the two nuclei. So destructive interference is not going to tend to form bonds. So adding them together results in a smaller magnitude. Where they overlap. So then we could fill in the blanks on the next page when two wave functions destructively interfere. The magnitude of psi decreases. So if you decrease the magnitude of psi, the value of psi squared also decreases. And a smaller value of psi squared is going to correspond to what in terms of probability of finding the electron? It'll be less likely. So again, the shape of the orbital will change. If we're less likely to find the electron there, essentially our orbital, our picture of the orbital, will shrink in that area, and it'll have to grow elsewhere. Pardon? So the question about what we call phase of the orbitals, or the phase of the wave function. So when we talk about the wave function, we say it either has positive phase or negative phase, meaning it's got a positive value or a negative value. Those values are kind of arbitrary. If you go back to lecture 2 and look, and we did bring up that term node, and the idea is the sign has to switch whenever you go through a node, so it'll always go from positive to negative when you go through a node in an orbital. But the way we represent that in our drawings of orbitals is to put in shading. So I didn't put in shading earlier here where I drew a p orbital, but a p orbital has these two lobes, and one of them would have positive phase and one of them would have negative phase. So usually when we draw a p orbital, we shade in one side of it, because there's a node right down the middle, and when you cross that node, the wave function goes from positive to negative. With the d orbital, there's two nodes, and so we would shade one lobe here and one lobe over there, so that each time we cross the node, we go from positive to negative. Graphically, the idea is whenever a function goes through 0, generally it goes from being positive to negative, because it's going through 0. But as far as whether like each orbital has a designated wave function sign, like 1s, is that always positive or always negative? My answer is it depends. When you're combining the orbitals, you have to make some arbitrary decisions about whether you're bringing them together in phase or out of phase. And yeah, there's a set of rules to go along with that. But I'll kind of touch on that in a couple minutes. So the question is, does that mean it depends on what side of the atom it comes from? No, because the orbitals, remember, are theoretical constructs. So orbitals don't have a set phase or a set orientation like within the atom. Really, we have to impose an orientation on them when we imagine the two atoms coming together. And usually, essentially, our rules for combining orbitals tell us that if we imagine them coming together with one orientation, we have to also imagine them coming together from the opposite orientation. And now I'm getting really abstract. So I want to get to some examples to hopefully make some sense of it. So the question is, are nodes a point in space or a plane? Well, there are two kinds. Angular nodes would be a plane. So the node here that I drew in the middle of the p orbital, or the two in the d orbital, those are angular nodes. Those are planes. But they're also what we call radial nodes that are spheres. If you go back to lecture 2, I talked about that and showed some pictures. All right. So that's a little background on how we combine orbitals. Now, one thing you're going to be asked to do is know something about what we call hybridized orbitals. Hybridized orbitals are orbital combinations. And so just to give you a little idea of why we have to come up with these things called hybrid orbitals. Think of a CH4 molecule. What would its shape be? Well, CH4 has this Lewis structure. To use the terminology that you'll see in lecture 5, this has 4 electron domains. So it'll have a tetrahedral shape. So when I want to draw CH4, I draw it like this. That wedged kind of line, that's showing that that hydrogen's coming out of the board, and the dashed line is showing that that hydrogen is going back into the board. But this is a tetrahedral shape. Now the problem is, if I'm trying to create a tetrahedral molecule like CH4, and I think about the valence orbitals, which Show asked about which orbitals are involved in bonding, it'll be whichever ones are in the valence energy level. So for carbon, the valence energy level is energy level 2. So in energy level 2, I have the 2s orbital, which looks like this. And then I have 3 2p orbitals. The 3 2p orbitals are all perpendicular to each other. So we'd have one 2p orbital that looked like this, one 2p orbital that looked like that, and then one 2p orbital that's kind of going into and out of the page. And they get called 2px, 2py, 2pz. So the need to think about hybridization comes from the fact that if I look at the shape of CH4, and then I look at the shapes of the 4 orbitals I have available, are those 4 orbitals pointing towards the 4 hydrogen atoms? No. It would be really convenient if I had a carbon atom with 1 orbital pointed towards each hydrogen atom. But that's not what I have. I have these 4 orbitals, the 2s and then the 2px, 2py, and 2pz, which aren't pointed towards those hydrogen atoms. So what we do is we take these 4 orbitals and we mathematically recombine them. We put them together in such a way that, well, if I add them up this way, I get an orbital pointed towards one of the hydrogens. And then I add them up another way, and I get an orbital pointed towards a second hydrogen, and a third, and the fourth. So we're going to recombine those orbitals into what we call hybrid orbitals that actually point towards the atoms they're bonded to. Okay, so that's where we're going to what we're going to do with them. We'll talk about 3 kinds of hybridization. This will be the last slide I do today. We can combine one of the s orbitals and one of the p orbitals to make what we call sp hybrid orbitals. So if I combine one s orbital and one p orbital, I get 2 sp hybrid orbitals. If I combine one s orbital and 2 p orbitals, I'll get 3 sp2 hybrid orbitals. And if I combine one s orbital with all 3 of the p orbitals, I'll get 4 new orbitals called sp3 hybrid orbitals. And so in the end, the one thing you're going to need to take away from all this is you're going to need to look at a molecule and be able to say which of these 3 kinds of hybridization it would have. So there's going to be a slide, let's see, like that slide. When we get there, that's the one slide you're going to need to know from the first half of this lecture. Okay? So just to put your mind at rest, all of this has been background so that if you choose, you can maybe understand that slide rather than just memorizing it. But in the end, if you just memorize it, you'll be okay.